We kind of warmed up with a simple problem that we did with power series to solve for it, and we got a solution without using power series, and then we confirmed our solution using power series. And so what we're going to do is we're going to dive into it now, where we're just going to do a bunch of problems. And so our main goal today is to be able to transform your differential equation into power series form, and then play around with the indices, with the index of these things. And so the trick is to match the index and combine the terms using matched indices. So let's dive into a couple of theory discussions about power series. And here's a definition. So an ordinary point is essentially a nice point. It's a point that's doesn't have a zero in the denominator that explodes or anything like that. Those types of points where you have zeros in the denominators are called singular, and that's a special thing that we're going to have to study in the next section. But for now, let's talk about ordinary points. So we're going to look at different orders of differential equations, but our main focus will be a second order differential equation. I think that's going to be difficult enough for us to deal with. So we have a second order differential equation. It's linear, and the coefficients don't have to be constants, but when we start off, they'll be constant coefficients. And so x naught is said to be an ordinary point of the differential equation if after you divide out that term, the leading function, a2, so that your leading coefficient for your differential equation is 1. So these p and q functions are analytic at 0, at x sub 0. And it's really, for us, to really simplify things, we're just going to look at x sub 0 is equal to 0. So we're going to focus mainly on Maclaurin series. So the point is not ordinary. It's said to be a singular point. And again, that's what we're going to study later on. All right? So that's just a term that we're going to throw around, ordinary versus singular. And ordinary just means it's a nice number. So the radius of convergence comes into play now in our next theorem. And the radius of convergence is the same idea behind the radius of convergence that we looked at in Calc 2. If we have an ordinary point, x naught is an ordinary point to the differential equation, then we can always find two linearly independent solutions for the second order differential equation in the form of a power series centered at x sub 0. So that is, we'll get y is equal to this thing, a power series solution that converges in some interval defined by x minus x naught less than r, and r is the distance from x sub 0 to the closest singular point. What? So without actually doing an example of this, let me see if I can refer back to our Maclaurin series, or a handful of series that we talked about last week, when we said, what's that series called? 1 plus x squared plus x cubed plus x to the third. Oh, that's x cubed, x to the fourth. What is? Remember what that is? What? No. That's the e to the x is divided by Geometric series. So let's take a look at the geometric series as an example for this thing. So this business about defined by x minus x naught, absolute value of that less than r. So it means it converges for all those points in there. So an accompanying picture might look like this. We have 0 as your center point. And then if we take a look at that geometric series, this thing has a particular radius of convergence. The radius of convergence is r. So r is some distance from x naught to the closest singular point. So remember that this turned bad when x is equal to 1. So we can say x is equal to 1 for us here is a singular point. So we know that the function, the series, is not going to converge here at all. Right? So this distance over here will be our distance r, and in this particular case r is equal to 1. So that means x, for any other x values, and I'll put the x values in green, so these other x values, as long as you're fairly close enough to x sub 0, which is 0 in our case, then it's going to converge for all those x values. So more specifically, we have x minus x naught is less than 1. So any distance from 0 to 1 in either direction as long as that distance is less than 1 from 0, then it's going to converge. So we'll converge here where the absolute value of x minus 0 is less than 1. So if you work this out, absolute value of x less than 1 is the same thing as saying x is between -1 and +1, right? You guys did that in like algebra. So those are the places where this thing is going to converge, and that's what this is saying over here. And your closest singular value, your closest bad point in this particular example is 1. So remember, I kind of pointed this out last week, that if you hit a singular value, if you hit a bad point going in one direction, that means you're going to hit a bad point going in the other direction as well. And what that means now is going to not converge, it's going to diverge everywhere else. It kind of makes sense for this thing to diverge on this side because this is your singular point, right? It can't go past that point because there's a break here. But the weird part is there's no break here. Your function is continuous on this side, but yet your series is only going to work up to this point. And it's not going to converge here. It's going to diverge here as well. So that's the interesting thing about the radius of convergence, is that when you hit a bad point on one side, even though there's no bad point on the other side, it's still going to only converge up to as far as whatever that distance is where you hit your bad point. So that whole idea of radius of convergence really makes a lot more sense in this context when we're looking for when this is going to converge than it did in Calc 2. You know, it's important in Calc 2 also, but it becomes a little bit more important here. Now, if we take this to represent not just real numbers but complex numbers, then the whole idea of radius of convergence makes a lot more sense because we're actually looking at circles where it converges, because we're looking at the complex plane as a two-dimensional set of numbers that we're using. But we're not going to go there. So that's the idea behind this theorem. Okay, so let's take a look at an example maybe. Suppose we should do an example. Let's do another example of a differential equation that we should know the solution to. So let's make up a second order differential equation that we know the solution to. And this one should be familiar. Let's see if we can come up with two solutions. Or let's put, should we put 4? No, let's just put y. It's going to get too complicated. So this thing, do we know the solution to this thing? Do you know off the top of your head by now? What is this solution? Yeah. So sine and cosine, right? C1 sine x plus C2 cosine x, or sine and cosine switched, or whatever. But this is a sine and cosine combination. So let's just put that down as something that we know already. Solution is going to be C1 cosine x plus C2 sine x. Okay? If you don't know that by now, you should just go through it really quick. There's finding the auxiliary equation, and then you can figure it out quickly from there. This is homogeneous, so we don't need to worry about anything else besides that. All right, so we know that this is a solution, but let's go through the process of power series to see if we can get the same thing. All right, we'll begin by assuming that your solution is represented by a power series. So solution is given by y is equal to some power series. K goes from 0 to infinity of c sub k times x to the k. And we'll assume that we're going to find a solution that's centered around x is equal to 0. So in the theorems that we'll see in the book, we'll see x minus x naught a lot, x minus x naught to the k power. But let's just assume that x naught is equal to 0 to simplify our problem. There's going to be rare cases where it might be singular at 0, and then we might need to move to another point. But for now, let's worry about when x naught is equal to 0. So we got the y here, but we need the second derivative of this. So let's take the derivative twice, and let's take the derivative first derivative first. And we're going to do this without writing out the terms like we did last time. We wrote out the terms last time so we can kind of get used to it, but eventually you'll need to go a little bit quicker than that and be able to do this, without having to write the terms. Now the derivative of this thing with respect to x is c and k. K is just an index. Ck is a constant, or they're all a bunch of constants. So I'll put the index down. Ck x to the k minus 1. That seems to make sense, right, as our derivative. Now our index started with k is equal to 0, but when k is equal to 0, you'll see that this whole thing disappeared, right? And that makes sense, because if we had written this out, we have c sub 0, and the derivative of that is that's just a constant. That's your first term. The derivative of that is 0. So we don't need to include the 0 term. And so we'll start with k is equal to 1. So you see that there's a shift here now, right? And we'll do the same thing to get the second derivative. And we'll have k minus 1, c to the k, x to the k minus 2. And for the same reason, when k is equal to 1, that thing's gone, so it would really make a lot more sense if we start with k is equal to 2. Okay? We're diving in. All right, so now let's put this differential equations together. We have y double prime, so let's write down our y double prime. We get the sum as k goes from 2 to infinity. And writing the sum is important because we need to know the starting point. That's going to make a difference when we set things up. We got k minus 1, c sub k, x to the k minus 2, plus we have a y, and that's just the original assumed solution going from 0 to infinity of c sub k, x to the k is equal to 0. So this thing's equal to 0, which means we're going to match up the coefficients, which means we need to combine this into one summation if we can. We should be able to. And what we need to do is we need to match the powers of x. So this is where you start playing with indices. Now, we can write this down, and we should write it down the first couple of times that we do this. Is it turning blue?
Yep.
Some issues with the connection here. Now, if I just not move it. Yeah, I'm sure it's been used and overused a bunch of times, so just have to be careful. All right, so let me write down the first few terms of this this one. When it starts off with k is equal to 2, so I have 2 times 1 c sub 2 x to the 2 0. Just knock that out. Plus, now k is equal to 3 is our next term, so this is 3 times 2 c sub 3 x to the first power plus the next one is k is equal to 4. 4 times 3 c to the fourth x to the 4 minus 2 is to the second power. I need more room. So that's the first sum. Let's see how the second sum is going to look like, and we'll see how to match things up. So this is the first sum right here, and the second sum is just the original one. So c sub 0 plus c sub 1x plus c sub 2x squared plus, I think we should be good with that. And as we look at this, we see that there are matching x powers. Right? So we should be able to combine this into one thing. So let's see how it would look like as we had written it out. We have constant terms over here, 2 times C2 plus C0. That's your first constant terms. The second one, 2 times 3, that's 3 times 2, C sub 3 plus C sub 1 times x. So I combined linear terms and I factored out the x. That's the one with a double underline, and the one with single underline looks like 4 times 3 c sub 4 plus c sub 2 x squared. So from here, we should be able to find a pattern, but my challenge to you is to try to come up with a pattern from the summation sign without writing these things out. And the idea is to be able to combine this into a single summation. So let's see if we could do that coming from the sum here. The powers don't match, but if I shift the powers a little bit, I might be able to find the matching powers. What? Okay, here's my deal. I generally like to have the powers to be the same here so that I can combine them, right? So what if I attempt to make this a k? So what do I do? So for each of these things, I want this to be k. So I'm kind of, I don't know how to put this. I want to replace k with k plus 2. That would make this into k plus 2 minus 2, which is just k, right? Maybe I should be using different variables for this. So if I think about doing a k, replace inside here, everything with a k, replace it with k plus 2, then my terms will change. Okay? So let's see what will happen if I do that. So I'll replace this with a k plus 2, and this would be k plus 2 minus 1, k plus 1, and the subscript here, k, would be k plus 2, and then I have x to the k. Right? Now that's great because now my second summation has the same power and has a matching power. What did I leave out? I left something out in this, I mean, equals 0. I left something out here purposely. What did I leave out? So first summation. Now, if you do that shift, right, with a k, if you do that shift inside of the summation sign, you're going to need to shift the starting point as well. So think about when you add something to the k inside of the summation sign, you're going to do the opposite for the starting point. So instead of starting with 2, do I start with 0 or do I start with 4? I start with 0. So a shift, a plus 2 inside, means there's a shift in the starting point as well. So your shift will be a minus 2. Okay? So aside from writing out the terms, which will take a few extra steps, a few extra minutes, valuable minutes of your time, think about doing the shift with the index. So this is the index shift for your summation signs. And this is about the trickiest part in the power series. Oh, this is just one tricky part. We'll see another tricky part after we get through this. All right, we good with this? So now that we have the same starting point, we can combine this. If we had different starting points, by the way, we can just take some of those stragglers out and then pick up for, we'll see if we can find examples of where the different starting points might happen. But in this case, we have k is equal to 0, k is equal to 0 summation. And so we can put this into one sum, k is equal to 0, and I'll just copy everything else and add them. So k plus 2, k plus 1, c sub k plus 2 times x to the k. Now, instead of writing x to the k there, I'm going to have x to the k over here that I'm going to factor out anyway. So I will take this x to the k and factor it out. So what just happened here? What happened was I took the coefficient of x to the k from the first sum and the coefficient for x to the k from the second sum, and then I combined them with the same index, starting index, and now the x to the k has the same power. So this is what I would have. Okay? Great. Beautiful. This is equal to 0. All right. So that's the first part. Oh, sorry. This is where these things, do you guys read the notes? If it's a long page, it's still okay to read, or should I go on to the next slide? There's another like this length of work to do. Stay on this slide? Okay, we'll stay on this slide. All right. So now this is what we have. And what we want to try to do is we want to try to find a pattern to see if we can get a pattern. If we don't get a pattern, then we should at least be able to identify the first few terms of this series. So what we're going to want to do is we're going to want to essentially solve for C sub 0, C sub 1, C sub 2, C sub 3. That's a lot to solve for, right? So the idea is to see if we can find a pattern. So let's see. I'm sorry, yeah, C sub 1, C sub 2, C sub 3. And in order to do that, what we're going to do is we're going to take a look at a bunch of k values and see what kind of patterns we see. Note that this is all set equal to 0, and because this is all set equal to 0, it's identifying the coefficients of these things are all going to be set equal to 0. So that means every single one of these things will be equal to 0 for different values of k. So we'll start off when k is equal to 0. When k is equal to 0, what do we have? We have 2 times 1 times c sub 2 plus c sub 0. And that's the coefficient of x to the k, or x to the 0. And I match that up with a coefficient of x to the 0, and that's going to be 0. And we'll see that for this thing, it's all going to be 0. All right. Well, you know your arbitrary coefficients C1 and C2 when we wrote this arbitrary coefficients. Chances are we're going to look at our arbitrary coefficients of C sub 0 and C sub 1 for these problems. And so given that this is an arbitrary coefficient, what we're going to be interested in doing is finding the C values that are bigger than that. So I want to solve for C2, essentially. So C2 is going to equal to, I subtract C1 or C0 over to the other side, and now we divide by 2. So it looks like C2 is going to be negative C1 over 2. Is that cool? Oh, it's negative C0 over 2, yeah. All right, let's box this. We're going to box a whole bunch of things. K is equal to 1. Let's see what we're going to come up with that. So when k is equal to 1, I have 1 plus 2, that's 3, times 1 plus 1 is 2. C sub 1 plus 2 is 3, C sub 3, plus C sub 1. And that is supposedly equal to 0. All right, so again, I want to solve for the larger C sub. So I'm going to say C sub 3 is equal to, I'll bring the C sub 1 over to the other side and divide by 3 times 2. And I have a feeling that this is going to be a pattern of some sort. So instead of multiplying and getting 6, I'll just say 3 times 2. Because I have this gut feeling that a factorial might be coming into play. Okay, let's box this guy. All right, let's keep going. K is equal to 2. So we haven't found a pattern yet. We got C sub 0 and C sub 1 working on their own thing separately. And that kind of makes sense to us because those are probably going to be our two arbitrary constants. So we want to build from there and see what happens. So let's say K is equal to 2 this time. I got 4. That's 2 plus 2 is 4. 2 plus 1 is 3. 2 plus 2 is 4, so that's C sub 4. Plus our C sub k, and k is equal to 2, so C sub 2. And this is supposed to be equal to 0. All right, what is that? I want to solve for C sub 4. C sub 4 is equal to, looks like it's negative C sub 2 over 4 times 3. What's C sub 2? Oh, C sub 2 is up here. It's negative. So negative C sub 2, negative C sub 0 over 2 divided by 4 times 3. Let's see. That simplifies to a positive. C sub 0 and the 2 goes down in the denominator. Let's call that 4 times 3 times 2. I'm going to rewrite C sub 4 here because this long set of inequalities might be too confusing. So now we have C sub 4 is equal to this. I suppose we should just call that 4 factorial, right? Can you see it? Is it coming? Can you feel it? So if we do one more, we could probably begin to identify a pattern. And let's see where this is going to take us. We have k is equal to 3 now. It's 3 plus 2 is 5. So we got 5 times 3 plus 1 is 4. Whoops. C sub, add 2 to that, C sub 5 plus C sub 1. Oops, I'm sorry, C sub 3. So this is where we're going to find a connection now with C sub 1, because C sub 3 is something with a C sub 1 in it. This is equal to 0, so I want to solve for the 5. C sub 5 is equal to negative C sub 3 divided by 5 times 4. C sub 3 is equal to negative C sub 1 divided by 3 times 2. And then we have 5 times 4. And so you see where this is going. Negative, negative is a positive. We have C sub 1 in the numerator. 5 times 4 times 3 times 2 is 5 factorial. So we kind of see a relationship between the odd indices and the even indices. And then we see that this is alternating. So let's see if we can start putting this together. Your solution is supposed to be y is equal to the sum of k goes from 0 to infinity of c sub k x to the k. And so this is actually c sub 0 plus c sub 1 times x plus c sub 2 times x squared plus c sub 3 times x cubed. I think we can go all over c sub 5 here. C sub 4, x to the 4th, c sub 5, x to the 5th. Whoops. All right. So c sub 0, it's just C sub 0. We can't really do anything about that. We just saw the C sub 0. C sub 1 is C sub 1. We also can't do anything about that. But now, in the solutions that we found here, and hopefully we're beginning to find a pattern, we can see that these things have these particular solutions for C sub 2, C sub 3, C sub 4, C sub 5, and presumably everything else after that. So what is C sub 2 equal to? C sub 2 is C sub 0 divided by 2. And so that gets multiplied with x squared. C sub 3 is a negative C1 divided by 3 factorial, x to the third. Let's keep going. We got C sub 4. C sub 4 is actually equal to C sub 0 divided by 4 factorial, x to the fourth. And C sub 5 is C sub 1 divided by 5 factorial times x to the fifth. These ones were not negative because when we solved for C sub 5, we got a negative C sub 3, but C sub 3 was negative, so that canceled out and became a positive. Now, clearly, there's a relationship here. Let me see that. Can't even see that. We got the C sub 0s going on, the C sub 1s going on for the odd and even values. So maybe it might be good to separate these into two sums. So let's gather the C sub 0s together and factor it out. So I'm going to do that in one step. I'm going to factor out a C sub 0 from all the terms that are all C sub 0s, and then let's see what we get. So I have a constant, so that will leave me with a 1. I have a minus x squared over 2. You can put an exclamation point there if you want, because that's the same thing as being 2. And then plus the C sub 0 is factored. I get x to the fourth over 4 factorial. And then I would imagine plus or minus whatever comes next. Well, no, it'll keep alternating. So the next one's negative, and the next one's positive. And if you're unsure of that, we can do one more here. K is equal to 4. And for some of these things, you might need to do K is equal to 6 or 8 just to get a feel for what's going on. In this particular example, we know the answer, so we know more or less what to expect here. But in general, you might not know what the answer is, so it could be a little trickier. So gathering all the C sub 0s and then gathering all the C sub 1s, we can see that split up. And C sub 1, the first one has an x attached to it. The second one is a negative. C sub 1 factored out, I get x cubed over 3 factorial. And then the next one has a C sub 1 positive, C sub 1 factored out, x to the fifth over 5 factorial. And then minus alternating signs. And then you see that these things are familiar to us, right? Because you memorized the series for sine and cosine. So this looks like an even function, alternating. You got the power matches with a factorial in the bottom, and we start off with 1, so this must be the cosine function. Second one is an odd function, matching powers and factorials, denominators, and then we have an alternating series. So this one must be the sine function. Then you're not going to be able to identify it. So in general, these series that you'll see here, even if you find a pattern, might not look familiar, might not be a familiar series that you already know. In this case, because the problem was just, sine and cosine, that was easy enough to identify. Had it been sine 2x, cosine 2x, you might still be able to identify it, but it would be a little bit more difficult. Now let's call it a lot more difficult. But you can still try to identify it. But in general, you might not be able to identify your series, so you would just write the series. If you can find a pattern, great, then you're lucky. Then that must have been an easy problem. But in general, you might not even be able to find a pattern, so you would just write down the first few terms of the series and say, oh, that's all I can do. All right. So, in terms of the convergence of this thing, we noticed that our original function, our original DE looks like this, going back to our original differential equation. We have y double prime, or let me just ask you this. If this is written in standard form, where the coefficient of the y double prime is 1, we would like to identify, I'd like to identify what P and Q are. Can you tell what P and Q are just by looking at this? The P and Q refers to the coefficients, the function coefficients of the y prime and the y. So what's P in this case? Looks like P is equal to 0. What's Q in this case? 1. So it looks like it's analytic around 0. Let's do this in a different color. Analytic at x naught is equal to 0. That's our center point that we used. We use that because this is the Maclaurin series. And then we also note that, does this have any singular points? Does it have any bad points anywhere? No singular points. So what can you say about the radius of convergence for this? How far can my interval go from 0? Positive or negative? What? It can go all the way to infinity, right? There's no break points, there's no bad points here, so my convergence is going to be for all real numbers. So no singular points, it means r equals infinity, radius of convergence. Convergence is infinity. So that means this must be good for all real numbers. Okay? Well, it depends on how they ask in the homework. If they ask for the radius of convergence, you just say r equals infinity. Or they say r equals blank, and then you fill in infinity. If they ask for an actual interval, then your interval would be whatever you would write for your interval. Okay, so we didn't talk too much about the interval of convergence, because when we talk about the interval of convergence, in this case it's infinite, so it's not an issue, but in general, the interval of convergence is going to depend on whether the endpoints also converge. And we had some examples when we talked about the geometric series last time. We had some examples where the geometric series didn't converge at the endpoints, -1 and 1, but then we had an ln function that looks like it converged at one endpoint but not the other. And we had an arctan where it looks like it converged for both endpoints. So it's trickier to identify the interval of convergence because we're looking at series that we may or may not know the closed function form. So, all right. So this is how you're going to be spending your differential equations life for a while. You're going to match indices. That's the first obstacle. The second obstacle is to do this, to find your pattern. Writing down k is equal to 1, 2, 3, 4, 5. Might have to go up to 8 for some of these problems. And then once you do that, figuring out how your series is going to look like. Have fun. All right, let's see what's next. Ordinary points, singular points. Now let's do some problems. Well, we just did a problem. Let's do another problem. This is differential equations, right? All right, let's do something like number 2 here, multiple choice. So our differential equation is y double prime plus x squared y prime plus x times y is equal to 0. So this is not, unfortunately, not a Cauchy Euler equation, so we don't have a nice technique for this. It's not, it doesn't have constant coefficients, so we can't just do the auxiliary equation. So we're kind of stuck here. We can't solve for this with any other techniques that we've learned so far. So let's go into power series mode. We have our differential equation already written in standard form, which is great. We can identify our P and Q from the beginning. P of x is equal to x squared. Q of x is equal to x. So these are all nice. These are nice functions, and 0 is a nice point. I don't have any issues about any singular points. No singular points. So it looks like my radius of convergence will probably be infinite for this. If I had my leading coefficient was an x or something like that, or an x minus 2, and if I divide that out, then I would have x minus 2 as in the denominator, and then 2 might be a singular point. But in this case, I don't have any singular points, so that's great. So let's begin doing this problem. How should we start? We should start by letting y, our solution, equal to c sub k, x sub k. K goes from 0 to infinity. That's how we always start our problems. We need our first and second derivatives. Y prime is equal to k. And remember, the derivative, we start with 1 now. And then our double prime is the second derivative. And again, our index changes. We start with 2. All right, let's take all those derivatives and put them into the original differential equation and see what we get. We got k goes from 2 to infinity, k minus 1, c sub k, x sub to the k minus 2. That's your first, that's your second derivative, that's your first term. And then now we have an x squared that we're going to multiply through, so our power for x is going to change here. K goes from 1 to infinity, and then our first derivative is k, ck, x to the k minus 1. This is our y prime. And then now we have an x times y, and y is just the original ck x to the k. And fortunately, this is a homogeneous differential equation, so we're going to set everything equal to 0. All right, before we mess around with the index, we have a couple of terms that are hanging outside of those summation signs that we need to incorporate in. So let's do that. Let's bring this x squared in and this x in, so our powers for those will change. So let me rewrite the first term. Now the second term, I'll incorporate the x squared in here. So this becomes x to the k minus 1, add 2 to that. So what does that become? K plus 1. And the last one, starting from 0 to infinity, we got c sub k, x to the k plus 1 again. All right, I have a couple of k plus 1s here, so looks like we might be interested in moving towards that direction, making it to k plus 1, or we could just write it as x to the k and see what happens and do the index shift. What should we do? Let's try to write everything as x to the k. All right? Write everything as x to the k. What's that mean? So for this one, to write this as x to the k, I want to change my k to k plus 2, right? Add 2. And that means I need to subtract 2 from the index. So subtract 2 from the index. I actually start with 0 to infinity. Now I have to add 2 to all the k's that I see here. I got k plus 2, k plus 1, c sub k plus 2, x to the k. All right? So I actually didn't change this whole expression, the first term here. If I were to write out the first few terms of this, and I were to write out the first few terms of the original form, I should get the exact same thing. Same coefficients, same subscripts, same powers. I should get the exact same thing. And that's the whole point here. I'm just shifting the index and changing the inside so that the expression remains the same. All right, now for the second one, I want to match this up with the x to the k as well. So I want to subtract 1 maybe, or add 1, subtract 1. K, change my k into k minus 1. So I'm subtracting 1. Inside, what do I do with the index? So I have to add 1. The index. Let's see how this is going to look like. Add 1, I start with 2 now. K goes from 2 to infinity. I have to subtract 1. I have k minus 1, c sub k minus 1, x to the k. All right. So now the last one, I would need to do the same shifting, same as this to match the powers. K, I have to subtract 1, and so I have to add 1 to the starting point. And so my starting point now will be 1 to infinity, and now I have to subtract 1, c sub k minus 1, x to the k. Okay, so far? All right. Now, we have some bit of bad news here in that we can't combine these things because they have different indices. So like last time I had started k start with 0, k start with 0, and so I was able to combine them. But now I can't combine it because they're starting from three different points here. So what we need to do in order to deal with this is rewrite the sums so that they start all in the same place. Now, wait, that doesn't make sense because we just rewrote the sum so that they have the same power, and so the index shifted. So instead of doing that, maybe I can take out a couple of terms here. Maybe I want to take out the term when k is equal to 0 and k is equal to 1 from the first term separately, and then I'll start with k is equal to 2. How should I write this? 2 to infinity. Sure, that'll work. All right, what do I mean by that? I mean, I want to write out, I don't want to write out everything, but see if I write down the first couple of terms, k is equal to 0 and k is equal to 1 from this first summation. What I could do is I can write out those first couple of terms and take them out of the summation, so my summation starts from 2. So when k is equal to 0, I have 0 times 2, or 0 plus 2 is 0 plus 1, so that's 2 times 1 times c sub 2, x to the 0 power, so that's just constant. So that's the first term for this sum. When k is equal to 1, that's your second term for the sum. When k is equal to 1, I have 3 times 2 times c sub 3, k is equal to 1, so I have a subscript of 3, and x to the first power. And then, now I can take care of the rest of the stuff. The rest of the stuff would be the series again. But now, the series starts at 2, because I took the first couple of terms out. All right, so this is going to have an x squared as my starting power for the series. So for the next one, it's already starting with the same index as the starting point as this first series that we just took apart. So let's just keep that because it already has a starting series of 2. Now the other one doesn't start at 2. It starts at 1. But if I take that leading term out, when k is equal to 1, then that would be a separate value or separate term, and then I can have the rest of the series happening here. So when k is equal to 1, I have c sub 1 minus 1, c sub 0, x to the first power. And then I would have the rest of this, except now I get to start at 2. Okay? So now all these summations, all these sums, all begin with x squared. That means the constant and the linear terms are outside, and so we're going to deal with those things separately. So what I'm going to do is I'm going to underline the constant term. There's only one constant term, yeah? And I'm going to double underline the linear terms. Because remember that I want this to equal to 0 constant, 0 times the linear, 0 times the quadratic, etc. So I'm going to set these coefficients all equal to 0. And then, starting with my quadratic term, I can start using the summation. Actually, let me write this down in one more step, just to make that a little bit clearer. So I have 2 times C2. That's the constant term, plus 3 times 2 times C3x, and then plus C sub 0. That's my linear term. And then I have the rest of them from my quadratic term on. So let me see if I can rewrite this into one big summation. What do I have? I have a big mess is what I have. I have k plus 2, k plus 1, c sub k plus 2, times x to the k, and k starts at 2. I will factor out an x to the k, because all these summation signs have an x to the k. So my second sum contributes a k minus 1 times c sub k minus 1. And my third sum only contributes a c sub k minus 1. I suppose I can combine these two, huh? Let's combine those two. They both have c sub k minus 1 in them, and they have k plus 1, and then they just have a 1, so, or k minus 1, and then the plus 1. So I think that just leaves me with k, c sub 1. Do you agree that this is what happens here? All right. Set this all equal to 0. Then what? Then I have a 2 c sub 2 equal to 0, which means c sub 2 equal to 0. Now I have a 3 times 2 c sub 3 plus c sub 0 equal to 0. And I always want to solve for the bigger one. C sub 3 is equal to negative c sub 0 divided by 3 times 2. So it looks like there was a relationship between c sub 3 and c sub 0. Okay, so those are just from these two. Now I have to find the relationship when k starts from 2 and to see what other c values I can get out of this. So when k is equal to 2, this thing is going to be equal to 0. So k is equal to 2, I have 2 plus 2 is 4, 2 plus 1 is 3, c sub 4 plus 2, 2 minus 1 is 1, and that's supposed to be equal to 0. What does that give me? That should give me c sub 4 is equal to negative 2 c sub 1 divided by 4 times 3. Okay? So next one, k is equal to 3. We're just going to progress now from the summation sign. When k is equal to 3, I have 5 times 4 times c sub 5 plus k is equal to 3, so that's 3 c sub 2 equals 0. We know that c sub 2 is equal to 0, so I'm not even going to mess with this. So c sub 5 is just going to equal to something with a c sub 2 in it, so that looks like it's gone. All right, next, k is equal to 4. Let's see. 4. So this is 6 times 5 c sub 6 plus k is equal to 4, and 4 minus 1 is 3. So now we have c sub 6 equals to negative 4 c sub 3 divided by 6 times 5. We have c sub 3 somewhere. Oh, right here. So we have negative 4, negative c sub 0 divided by 3 times 2 divided by 6 times 5. It's not quite the, what do you call it, factorial. In fact, it's kind of messing us up a little bit. But this is a negative, negative, it's a positive. Let's say 4 c sub 0 divided by 6 times 5 times 3 times 2. But it's positive. Any ideas how to squeeze in a 4 in here? You multiply top and bottom by 4, right? You get 4 squared up on top, and this would become a 6 factorial on the bottom. So if we want, maybe, if we multiply top and bottom by 4, we're going to get a 4 squared c sub 0 divided by 6 factorial. Maybe. All right, I still don't see a pattern here, so let me do one more. Yeah, so we can get a factorial there, so 2 squared. All right, let's do one more. 5, we get, this is 7 times 6, c sub 7 plus 5, c sub 4 is equal to 0. So c sub 7 is equal to negative 5 over 7 times 6, c sub 4. and c sub 4 was equal to this thing, c sub 4 is equal to negative 2 c sub 1 divided by 4 times 3 divided by 7 times 6. And so negative negative is positive, so let's call it positive. We have 5 times 2 times c sub 1 divided by 7 times 6 times 4 times 3. So if we square the 5 and square the 2, we can get a 7 factorial down here. All right, so let's see. Let's take a look at the choices here. Oh, they didn't find factorials. They just multiplied everything out. Well, they have x to the 8th here. Our c subs over here, our c sub 7, we have this up to x to the 7th power. So we can, if we go one more, maybe two more, we can see where x to the 8th is. And then we can simplify all these values. So what do you say? Can you pick it up from here? Maybe, if you aren't so lost that you're kind of glazed over right now. It's past time, so we need to stop. So try to finish this up and then take a guess. I mean, find out the correct answer and then see what you get from there. All right, I told you this stuff is going to get really tedious, and we're going to do a lot of guessing and checking and stuff. So just be meticulous with your work. I should have your exams back to you by Thursday.